Finally, to end the section of lectures about stream ciphers, we take a look at a couple of stream ciphers used in the real world. We'll start with an older example, RC4 or ARC4. This cipher is getting a little old, but it can still be seen in the wild. For example, some web servers could still be using ARC4, so it's not like this is redundant just yet. ARC4 can encrypt data using different sizes of keys. Usually the smallest possible key is 128 bits long, but it does support smaller keys all the way down to 40 bits. It's possible to use different size keys because internally the key is expanded to 2048 bits regardless. Then this 2048-bit internal key is used to do the actual data processing. This random key is fed to a pseudo-random number generator, which produces random numbers 1 byte at a time. So for example, take you have a 128-bit key to start with. It's expanded to 2048 bits, which is then used as the generator's internal key. After the expansion, the pseudo-random number generator generates one random bit at a time. And the pseudo-random number generator is used as many times as it is necessary to get a lengthy enough bit stream for the stream cipher. We can tell that the ARC4 is an older design simply by looking at the weaknesses that have been uncovered during its time in production. There are three weaknesses especially that make the ARC4 not the best cipher there is. First, there's the bias in the generated bit stream. So remember, we have the pseudo-random number generator that is generating random numbers 1 byte at a time. If you remember, 1 byte is exactly 8 bits long. So let's say our random byte of data would be 1010 1010. So this example of random data is of course 8 random bits of data, which in decimal would be I think 170. Anyway, the idea behind a random byte of data is that each of these individual bits here are selected at random. So if you think about it, the byte of data can be or can get a value of anything between 0 and 256. Now if we select a byte at random from these 256 options, the probability for one byte to be selected should be, or one particular byte to be selected should be 1 over 256. And it turns out that the pseudo-random number generator that the ARC4 uses actually produces slightly biased bit streams. In particular, the second byte that you generate with this generator is very often 0, and very often means twice out of those 256 permutations. So whereas the correct value for this probability should be 1 over 256, if you inspect the output of the pseudo-random number generator, you actually end up with 2 over 256. And this is enough to make the cipher unsecure at times, or well, the pseudo-random number generator insecure. Of course, Knowing this bias, we can simply ignore the second byte and start using these random bytes from the third byte onwards. The random number generator in ARC4 actually exhibits another type of bias toward 0 bit streams. Particularly, it's surprisingly likely to find patterns of consecutive 0 bytes. And the probability for that, again, is not very much larger in terms of numbers as we are used to, but in the Cipher world, this is enough to make the selection of random numbers not reliable enough. So the actual probability of getting 2 consecutive 0 bytes should be 1 over 256 squared, because, well, again, in order to produce 2 0 bytes, which would look something like this in decimal or in base 10. So this is, of course, the same as having a bit stream that in binary would be 0, 0, 0, 0, 0, 0, 0, 0. And of course, because it's a pair of zeros, this is just 1 byte here. So we add another 8 zeros to the end. So this is the actual bit stream that the random number generator really likes to produce. And the probability, well, the bias that it exhibits is that there is another factor here, this 1 over 256 to the power of 3. So this is the actual bias. This is how much more likely it is to produce those consecutive to 0 bytes. And the final problem with the pseudo-random number generator with the ARC4 cipher is actually something that we already looked at. So the problem with using consecutive keys, as demonstrated in the previous lecture, in the web cipher system for Wi-Fi security. So even if you take into account the first 2 biases, which is toward 0 bits in the bit stream, the random number generator is only reliable if you initialize it using random initial keys. So you cannot use consecutive keys, as was demonstrated in the web example in the previous lecture. As an example of a modern stream cipher, we could look at eStream. eStream is not actually a stream cipher, but it's a portfolio consisting of multiple stream ciphers. In eStream's core, there is a pseudo-random number generator that works like the pseudo-random number generator in other ciphers. So it takes a short seed value of random bits and converts it into a long unpredictable bit stream where the output is much larger than the seed value. Where eStream differs in comparison to the ciphers looked at previously is the parameters for the pseudo-random number generator. One parameter is a one-time key, or a nonce, as Americans like to call it. So nonce standing for number used once. So this is the key used to encrypt the messages. And in addition to the one-time key, there is also a seed value. And in our formulas, the one-time key is denoted with a lowercase k, and the seed value is denoted with a lowercase r. Now, the encryption function for an eStream cipher is very similar to the one-time pad. So we have an encryption function with its 2 parameters. So there is the key to encrypt the message, and then there is a pair, there is the actual message to be encrypted, and also this seed value. So we feed them as a pair of parameters. So there is k is alone, and then there's the pair of m and r. And the actual encryption happens using the XOR function, just like in the one-time pad. The output of this function is the message XORed with whatever the pseudo-random number generator produces from this pair of parameters, and these parameters, of course, being the one-time key and the seed value. Now, what makes this cipher interesting is that we can actually use the same key multiple times. This is because the pair of parameters k and r here, well, the combination of a one-time key and a seed value makes this pair unique. So it's actually possible to use the same original key multiple times, and this can be advantageous. So the only requirement is that each key and seed value pair is only used once, but we can reuse a key multiple times. An example of one cipher in the eStream portfolio could be the Salsa 20. So Salsa 20 is an interesting cipher because it comes with both a software and a hardware implementation. That means that it's a relatively easy function to construct, and it can be built directly in hardware. Salsa 20 uses either a 256-bit key or a 128-bit key. The encryption function Salsa 20 generates a long pseudo-random bit stream, as long as it is necessary, by using a function that's denoted here using h. And then, as you can see, h appears many times. So as said, we can use h many times, this function h, to encrypt all of our individual pieces of data, and we can keep using this function h until all of our data is encrypted. This h function actually uses three parameters. There's the one-time key k, there is the seed value or random value of r, and then there is also a counter n, which you can see from the previous two uses of the h function here and here. It's actually just counting how many times we have used this h function. And next we can look at how this h function actually works. So first we take all of the parameters that we received and expand those parameters from the 32 bytes that they use to 64 bytes. And this is done using some constant values. So for instance here T0 is a constant, here you are. T1 is a constant as well, and so is T2 and T3. And in this expansion there is nothing too mythical about it. It's simply padding this bit stream so that it emerges as a 64-byte bit stream from the original 32 bytes. Then we feed this expanded bit stream onto another function, which is here denoted with a lowercase h. And this is a function that basically takes in 64 bytes of data, and then the function itself simply maps these 64 bits of data onto another block of 64 bytes. And how it does this is by using a simple addition operation. The addition operation basically denoted with this plus sign here. And this is nothing magical either. It's simply adding certain characters onto the input data stream. And this basically means that if we were using letters as an example, basically we would be adding one letter from the input stream to another. So basically, like, let's say the input message contained A, and we wanted to run it through this function. What it would do, it would select another letter, let's say B, and the result of A plus B would be C or something in along that line. So it's basically incrementing the value or like summing those values together from the input stream. And this is simply repeated for about 10 times until we end up with a ciphered version of our data that is 64 bytes in size at the end. What is great about this h function, or this lowercase h, is that it is completely reversible. So that means that in order to decipher a message, all we would have to do is to run the function again on our original data. So basically this would stand, so running h using data that was produced by the same function, h actually gives you the original input back.